In this TA session, we are looking at the topic of polarization. For the warm-up problem, we look at the common situation where you take a balloon and you rub it on your hair and your shirt, and you touch it to a ceiling or a wall, and it sticks there. And the question is, why does it stick? We hope that they'll take this picture and draw that the charges on the balloon end up polarizing the atoms in the ceiling and the wall. So that if there's a negative charge on the balloon, it makes the atoms in the ceiling have their positive end toward the balloon, so that there's an attraction between the balloon and the ceiling. That's the idea, what you would like to see on the whiteboard. Next, we look at a more quantitative problem of the polarization of a conducting wire. So we're looking at how a conductor polarizes when you put it in a uniform electric field. Here we have a conductor, a wire, that stretches from minus L over 2 to plus L over 2 with an electric field pointing in the minus x direction. The first question is, or we assume that the electric field polarizes the wire so that we end up getting a charge of magnitude q at each end of the wire. Which end is positive and which end is negative? And what is the dipole moment that this creates? Well, we have the electric field pointing to the left, so the left end is going to be positive. The dipole moment is defined as the charge times the separation of the two charges. So it's Q times L. And it points from the negative charge to the positive charge, so it points in the same direction as the electric field, with a magnitude of Q times L. What is the polarizability in terms of L, Q, and E0? Well, polarizability is defined in terms of the applied electric field and the times the polarizability is equal to dipole moment. So P is equal to alpha times E0. So the applied electric field is E0, and the dipole moment is Q times L. So it's QL divided by E0 is equal to alpha. Next, we want them to think about the forces and the electric fields that are being generated by the applied uniform field and also the separated charges in this wire. So what is the force due to the electric fields on the negatively charged end of the wire? So that's the right end of the wire. Well, there are two electric fields. There's the applied uniform field that has a magnitude of E0. So the force due to that is Q times E0, pointing in the positive x direction. And then there's also the force due to the positive charges at the other end of the wire, which is attractive, so it's pointing in the negative x direction. And that's given by 1 over 4 pi epsilon naught times Q squared over the separation L squared. If you look at the force on the other end of the wire, is just the negative of what you got in part C. Both terms are negated. So that if you ask about the net force on the wire, the net force on the wire is 0. In the last problem for this TA session, we look at the polarization of a neutral atom. Here the situation is you have a neutral atom located at the origin, and a proton is placed on the positive x-axis at a distance r from the origin. And the atom has a known polarizability of alpha. We first want them to sketch the system. So it's important for them to draw it big enough on the whiteboard so they can actually see everything that they want to include in the problem. In particular, there must be enough room for the atom to be polarized so that you can actually see the electron cloud being stretched by the proton's electric field. And the electron cloud should stretch out in the positive x direction toward the positive charge of the proton. What is the magnitude and direction of the induced dipole moment P? Well, P points from the negative charge to the positive charge of a dipole. In this case, the electrons got stretched out in the positive direction, so going from the negative to the positive means that the P points in the negative direction, negative x direction. The magnitude is simply given by the definition of the polarizability, that P is equal to alpha times the applied electric field. In this case, the applied electric field is due to the proton, given simply by the 1 over 4 pi epsilon naught times the charge of the proton E divided by the distance squared, or r squared. What is then the magnitude and direction of the force on the proton due to the induced dipole moment? Here we're going to use the assumption that they should think about the assumption that the separation of the charges is very small compared to the distance r, or they can at least make that assumption. It makes it easier for them. We want the results to be in symbols, and there's two or three steps to this problem. Once you know the induced dipole moment, you can then use that induced dipole moment from B to calculate the electric field at the location of the proton. In this case, we're on the axis of the dipole moment, so the electric field is like 2 times the dipole moment divided by the distance to the proton, which is r, or in this case divided by r cubed. And then you have to multiply by the charge of the proton E to get the force. In the last part, you need to we ask them to plug in some numbers to just get an idea of what the sizes of this force on the proton. So the overall idea of this TA session is to look at the polarization of conductors and neutral atoms when they are placed in electric fields. We want them to draw pictures that clearly show how the polarization goes on, and we want them to be able to calculate the polarization and the forces due to induced dipoles. In the next 2 slides, you'll get to do some of the calculations that they'll be doing in the TA session.